So I would always remind you, everyone, to read the instructions when you're taking the exam. So this first question says, use L'Hopital's rule to find the limits. So the first limit is the limit as x goes to 0 of sine of 3x over tangent of 6x. So since the instruction said use L'Hopital's rule, we should just straight away use L'Hopital's rule. When we use L'Hopital's rule, it's important to do two things. Well, one of them anyway. It's very, very important. We shouldn't actually have to check, I guess, that it's a 0 over 0 or infinity over infinity type. I still think it's good to check. Even though he said to use L'Hopital's rule, I'm still going to check and see, okay, if I plug in 0, I'm going to get sine of 0, which is 0, over tangent of 0, which is also 0. So this is definitely a 0 over 0 type. So we're allowed to use L'Hopital's rule. And then I think it's worthwhile to write this L apostrophe H above your equal sign. Not absolutely necessary, but I think it's good practice. But what is absolutely necessary is that in this next step, before you do anything else, you write the limit as x approaches whatever it's approaching again. That is absolutely 100% required. And then we're going to take the derivative of the top and the derivative of the bottom. So the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. The derivative of tangent of some stuff is secant squared of that stuff times the derivative of the stuff. And then you might have to use L'Hopital's rule more than once, but every time immediately after using L'Hopital's rule, then you should try to, in your head, plug in what x is approaching and see if it works or not. Question? No, we should not change tangent to sine over cosine. Well, what's the benefit to doing it? So I will point out the benefit, nothing's going to cancel if we change tangent to sine over cosine, specifically because here it would be sine of 6x over cosine of 6x. So it's really not to our benefit. It's also much, much easier to directly take the derivative of tangent versus taking the derivative of sine over cosine. So no, we shouldn't change it in this case, at least. That's not to say there aren't other cases where you might want to change it. So here, if I plug in 0, cosine of 0 is 1, and secant of 0 is also 1. So we can go ahead and straight away say, oh, great, that's going to be cosine of 3 times 0 times 3 over secant squared of 6 times 0 times 6, which is just 1 times 3 over 1 times 6, which is 3 over 6, which is 1/2. It's definitely important to know that cosine of 0 is 0 and secant of 0 is also 0. Whoa. I just said the wrong thing. The cosine of 0 is, and secant of 0 is also 1. Not what I just said before. I'm not even going to repeat it. It's terrible I said that. I feel ashamed. Okay. Let's do the next one. Some trig stuff here. The limit as x approaches pi over 2 from the right of tangent of x minus secant of x. Now, the problem says to use L'Hopital's rule, and immediately right now we know we have to do something first, because I don't have, at least the way it's written, I don't have a fraction, right? You have to have a fraction to be able to use L'Hopital's rule. So this is an instance where I should rewrite tangent as sine over cosine. I should also rewrite secant as 1 over cosine, so that I have some sort of fraction. Also, if you plug in pi over 2, tangent of pi over 2 is undefined. Secant of pi over 2 is also undefined. So we're going to write this limit. X approaches pi over 2 from the right of sine of x over cosine of x. Now, if we were being wise about using our space here, we know that tangent is going to be sine over cosine and secant is going to be 1 over cosine. We should just skip, I think, to writing, instead of writing sine over cosine minus 1 over cosine, I think it's totally reasonable to have skipped that step and written it as the limit as x approaches pi over 2 from the right of sine of x minus 1 all over cosine of x. And here I am thinking I should do something like multiply by the conjugate because I've forgotten the instructions, right? I really was like, oh, I should multiply by sine of x plus 1. And I get like a trig identity on top. No, I shouldn't. I should follow the instructions. I should double check that I can use L'Hopital's rule. So I plug in pi over 2. Sine of pi over 2 is 1. 1 minus 1 is 0. And cosine of pi over 2 is 0. So we definitely have a 0 over 0 type. Now we can definitely should use L'Hopital's rule. So using L'Hopital's rule, it's going to be the limit as x approaches pi over 2 from the right Derivative of sine of x minus 1 is cosine of x minus 0 all over the derivative of cosine of x is negative sine of x. And then this should work out when we plug it in because cosine of pi over 2 is going to be 0 and negative sine of pi over 2 is going to be negative 1. So we get 0 divided by negative 1, which is 0. All right. More L'Hopital's rule. The limit as x approaches 0 of 1 plus 2x to the 1 over 3x. I will point out, just like the previous problem, we know we can't apply L'Hopital's rule immediately because it's not written as a fraction. You have to have a 0 over 0 or infinity over infinity to be able to use L'Hopital's rule. I'm not sure how he talked about this one in class. Did he talk about, so there's two schools of thought, which really amount to the same thing. You can either do it as the limit of e to the natural log of your stuff, or you can just take the limit of the natural log of your stuff, and then at the end of the process, then say your answer is e to whatever you got. That's probably gonna end this way. So I'm not gonna close it. So how did he talk about it? Did he talk about it as doing it as e to the natural log or as just the natural log? Okay, that's kind of the more typical way, which I prefer as well. So we're just going to rewrite this as the limit as x goes to 0 of e to the natural log of all of the stuff that's right there. Our 1 plus 2x raised to the power of 1 over 3x. So then we're going to, the whole reason for doing that is so that we can get this 1 over 3x as a power out of the power. So we're going to rewrite this as the limit as x goes to 0, e to the 1 over 3x times the natural log of 1 plus 2x. And I kind of did myself a disservice there. I really should have written that not as 1 over 3x times the natural log of 1 plus 2x, but as the natural log of 1 plus 2x divided by 3x. Right, because really I'm just thinking about bringing this down to the bottom, but bringing it down to the bottom, you flip 1 over 3x over and you just get 3x. Or 1 over something times something is just this thing divided by everything. So I'm going to do two things here. I'm going to rewrite that as the natural log of 1 plus 2x all divided by 3x. And then I don't think you need to do this next part, but I would encourage you to say, well, the limit of e to the stuff is going to be the same as e to the limit of the stuff. That's a totally acceptable thing to do. The rule about continuous functions, that if you have the limit of a continuous function, the limit kind of passes through to the inside of the continuous function. I'm not surprised. That's what I expected that he had done. So then we look over here, and now we can use L'Hopital's rule, because if you plug in 0 for x, 1 plus 0 is 1, and the natural log of 1 is 0, and 3 times 0 is 0. So this is definitely here. This part here is certainly a 0 over 0 type of limit. So great, we use L'Hopital's rule. We remember that it's e to the all this stuff, so we're going to write e to the limit as x approaches 0 of the derivative of the top over the derivative of the bottom. So the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, and the derivative of 1 plus 2x is just 2, and the derivative of 3x is just 3. Sometimes you need to simplify this. Not in this case, but sometimes there's like some -1 over x squared that cancel out each other. Here, we just plug in 0, and we get e to the 1 over 1 plus 0 times 2 over 3. So that's going to be e to the 2/3. Correct. No, definitely not. 0 divided by 0 is not equal to 0. So, and I want to point out, we just showed it, right? In this case, this 0 divided by 0 ended up being equal to 2/3. but there's lots of instances of a 0 divided by 0 not equaling 0. Here's another example. The limit as x approaches 3 of x squared minus 4x plus 3 over x squared minus 9. If we plug in 3 right now, that is certainly going to be 0 divided by 0, assuming I've done things correctly. Let's check. Plugging in 3, we get 9 minus 12 plus 3 over 9 minus 9, which is certainly 0 divided by 0. I want to strongly, really emphatically point out that this is not necessarily equal to 0. Occasionally it is, but that's the whole nature of this indeterminate form, is it can actually end up being any real value or not any real value, right? It might not exist at all. But if we look here, instead of using L'Hopital's rule, although we could use L'Hopital's rule, but instead of using L'Hopital's rule, we're going to factor. Okay, great. This is the limit as x approaches 3. Top factors as x minus 3 times x minus 1. The bottom factors as x minus 3 times x plus 3. If we cancel the x minus 3s and plug in 3 for the rest of the x's, we get 3 minus 1 over 3 plus 3, which is 2 over 6, which is 1/3. So just to kind of really, really, really strongly make sure that everyone's cool with the fact that 0 divided by 0 doesn't usually mean you get 0. It could occasionally, but you can't just assume that. You have to do more work. And that's really what I say. When I see a 0 over 0 type of limit, I say, oh, more work. I got to do something else. All right. Continuing on with this practice midterm 3 from Dedel. Problem 2. Here's what it says. Let the function f be defined as f of x equal to x to the 4th minus 2x cubed plus 2x minus 1. Find all intervals on which the graph of f is concave up and all intervals on which the graph of f is concave down, and determine all inflection points of f. So it's really important that we read that, because at this point, if I had just read the first part, I thought it was going to be like a graphing question. I was going to start finding the first derivative stuff and finding maxes and mins and finding the x-intercepts and the y-intercepts as well. So it's good that I read the question, because I was going to do more work than I needed to do. So reading the question, I'm just trying to find the concavity where it's concave up and concave down. So I'm looking at all the second derivative stuff. So I'm going to take my first derivative, because I have to take the first derivative to get to the second derivative. It's going to be 4x cubed minus 8x squared, minus what? Minus 6x squared plus 2. And I'm not going to bother setting that equal to 0 and trying to find my critical points, because that has nothing to do with concavity. Take my second derivative, which is going to be 12x squared minus 12x. And I'm going to set that equal to 0, because I want to find where the second derivative sign might change from negative to positive or positive to negative. Then we're going to factor as much as possible. So I'm going to factor out the 12x from both of those pieces. I'm left with an x there and a 1 there. So it looks like the points on my number line are going to be x equal to 0, x equal to 1. So here's the way I kind of prefer to do it. I just draw my number line and I put my critical points on there, my second derivative critical points, 0 and 1. If you like, you can say that infinity is over here and negative infinity is over here, although it's kind of implied. And then I'm looking at the sign of the second derivative. So picking a number larger than 1, like 3, 12 times 3 is positive, 3 minus 1 is positive, and the positive times positive is positive. And then you could either keep picking values, or you could use the fact that each of these critical points comes from factors that are raised to odd powers, which means the sign is going to change every time. So it should be plus, minus, plus. You could also pick like 1/2. Sometimes 1/2 is positive, 1/2 minus 1 is negative, and positive times negative is negative. And you can pick -2 and get a negative here and a negative here, so it's a positive overall. Yeah. Then the signs wouldn't change. Correct, it'd be positive, 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 all the signs for you. So it's always based on the parity of the power. So if the power is even, the sign stays the same. If the power is odd, the sign changes. So for example, just kind of like, for example, if I had something like x squared times x minus 1, sure, that's fine. My sign chart for my second derivative would look like this. So over here, it'd still be positive. At 1, we would change, and at 0, we wouldn't change. So that one would be concave down, concave up. Yeah.
Want to ask, when you do the concavity test for x squared, you have a 0 at 0, and so.
Whoa, let's hold on there.
Well, okay, for example, let's say it's the original.
But before we get on this other track, let's finish this problem real quick, and then I promise you we can look at that. So just to end this one here, we see that the function itself is concave up over here, concave down over here, concave up over here. So the question specifically asks to find all the intervals where the graph is concave up. So I would say it's concave up on the interval from -infinity to 0, union 1 to infinity, and it's concave down on the interval from 0 to 1. It also asks us to, find the inflection points. So if the just says find the inflection points, technically we should also find the y value. So we definitely have inflection points at both of those critical points, because both of those places are where the concavity changes. So you have an inflection point at x equal to 0 and y equal to f of 0, which is going to be just -1. So that would be the point 0, -1. And then also at x equal to 1 and y equal to f of 1, which is going to be 1 minus 2 plus 2 minus 1, which I think is 0. It seems right. 1 minus 2 is -1, plus 2 is +1, minus 5 is 0. So the other point would be at 1, 0. Those would be your inflection points. If you're asked to find the point, that means there's an x coordinate and a y coordinate. Yeah. Sure. This is the other second derivative. No, they're definitely not, because the concavity doesn't change, right? To have an inflection point, one of the requirements is that the concavity changes from positive to negative or negative to positive. Yes. Yes, so if the exponent is odd, then the sign is going to change when you cross from one side of the value that factor came from. So 1 came from x minus 1, the power was odd, the sign changed. 0 came from x, the power was odd, the sign changed. Whereas over here, 1 came from x minus 1, the power was odd, the sign changed. 0 came from x squared, the power was even, the sign stayed the same. So even powers, sign stays the same, odd powers, sign changes. Okay, now, do you have a question about this?
Oh, yeah, so for the concav, if you're talking about intervals for concav,
Mhm.
it's always parentheses, right? Not brackets.
Yes, and that's also true for increasing, decreasing. You should always have open intervals, not closed intervals. Okay, yes.
So I was gonna ask, because you just mentioned that when concavity, it does not change between the inflection point that we calculated, there's no inflection point.
So say that one more time.
So you said that concavity, or there's no inflection point, the concavity on the left and right side of the inflection point does not change, right?
Right, and so I would say, you can't say on the left and right side of the inflection point, though, because there isn't an inflection point there. You can say on the left and right side of the critical point. So if on the left side and the right side of this second derivative critical point, if the concavity doesn't change, there is not an inflection point.
But what if it's a cusp?
You cannot have an inflection point at a cusp, because one of the other requirements of an inflection point is that the first derivative exists there. And first derivative does not exist at a cusp. So yeah, there's this kind of weird thing about inflection points where basically the function has to be smooth. You cannot have a pointy point and have an inflection point, which some people actually disagree about this definition. Like some people think there should be an inflection point there. Like for example, if you draw something funky like this, like concave down up to there, and then concave up after that, not an inflection point, because the graph isn't differentiable at that point. That's too harsh though, because the graph isn't smooth there. And I really have to say that specifically, because there is another example, and we're getting kind of in the weeds here about this, like we should be not getting this specific. Well, I'll just say one more thing. The function x to the 1/3 does have an inflection point at the origin, even though the derivative is not defined there, because that's a vertical tangent line. But that's the way it's, if you like, let's look at the book. Do the book says. Which section is this? Like 3 point something? 3.6 maybe? No, I don't know. Where is this? Where is the section 4 point something? Yeah. 4.2. Concavity. See, did it define inflection point? See the word somewhere. So they say point's called an inflection point if f is continuous there and the curve changes from concave upward to concave downward or from concave down to concave up. I don't know about that definition there. I feel like that's a little bit dicey. So atypically, so to answer your question, in the context of this textbook, I am incorrect, and you are correct. So as far as this book is concerned, which I do not agree with personally, because that's not how I have learned it, is that technically this point here, D, they are saying is an inflection point. I heartily disagree, but because other textbooks have definitely defined it differently. So yeah, that's kind of weird to me. So I have to take it back. As far as this class is concerned, we would call that an inflection point. But it's not really what we think of as an inflection point. Because when you're thinking about an inflection point, you're kind of thinking about where the rate of change is kind of topping out, right? Like you're as steep as possible, and then you become less steep, like something that looks more like that. There's kind of your classic inflection point where the derivative is positive, less positive, 0, negative, as negative as possible, and then less negative, 0. Right, so the inflection point is usually where your rate of change is the most it can be, either negatively or positively. That's the more kind of classic, typical way of thinking of it. But I'm gonna have to talk to my coworkers about that. I don't love it. I'm not a fan. Oh well. I don't get to pick all the math. It's a good question. Yeah, thank you for asking that. I'm glad we looked. As far as the Dell is concerned, I wouldn't be too concerned with that particular idea coming up because he's very much of the mindset of myself as well, where he's taught other classes where it's been defined other ways, and I imagine that's how he still probably thinks of it, even though it's different in this book. How strange. Mean value theorem. Have you guys talked about the mean value theorem? You have? All right, let's do it then. So the mean value theorem, at least the idea of it, it's pretty straightforward. It just says that if the function is continuous and differentiable, meaning where you can take the derivative and the function is continuous, that the average rate of change, there's somewhere where the instantaneous rate of change is equal to the average rate of change. Or in other words, I like to think about is if you're driving somewhere, right, and you drive like from here to, I don't know, somewhere 100 miles away, and it takes you 2 hours, your average speed was 50 miles an hour. And that means that at some point, your actual speed had to be 50 miles an hour as well. You couldn't always be under 50, your average wouldn't be 50. You couldn't always be over 50, your average wouldn't be 50. At some point, you went from below 50 to above 50. So you had to actually hit a speed of 50 miles per hour. That's all the mean value theorem really says, is that somewhere your actual rate of change, your actual derivative, your actual instantaneous, whatever, is equal to the average over that period. So let's look at this question in that context. State the mean value theorem. Ugh. Okay. State the mean value theorem. So suppose, here's how I would write it. Suppose f of x is continuous on the closed interval from A to B and differentiable on the open interval from A to B. Then there has to be, or there must be, at least one, although there could be more, number, we usually call it C. And it is important to say that C lives between A and B. Such that, okay, we're just going to write the part now. And in fact, I want you all to write down this part, that the derivative is equal to the average rate of change. The derivative at C is equal to the slope of the secant line between A and B. See if you can write that down. I'll give you a second. Bless you. Graphically, that's what it kind of looks like. Somewhere on your interval between A and B, there has to be a place C where the derivative, the slope of the tangent line, is equal to the average rate of change. The slope of the line connecting the points from A to B. The way we write that is f prime of C equals f of B minus f of A divided by B minus A. That's the whole mean value theorem. But there's some point where the instantaneous rate of change is equal to the average rate of change. And that point has to be between your endpoints. Right? I can't say I average 50 miles an hour 3 hours after I was done doing my trip of 2 hours. That doesn't make sense as far as the problems. Questions about this? All right. There's really only like, there's okay, fine. There's like 2 varieties of questions we can ask, but one of them's more popular. So let's look at the second part of this question. This is part A for question number 3. Part B says, at what points C in the interval 0 to 1, so in 0 to 1, and at what points in the interval can you have it says you can have, I think he means, can you have a tangent line to the graph of, so in 0, 1, where can we have a tangent line to the graph of f of x equal to x squared plus 2x minus 1 parallel, meaning having the same slope as, to the secant line passing through the points 0, -1 and 1, 2. So we don't need to draw a picture here, although we could, but I think we should try to do it without drawing a picture because we just want to take the inputs they've given us and trying to figure out what we've got. Yes, I can. So here's what we're asking to do. We want to find a value in 0, 1. Where can we have, oh, and he says, he says, at what point C? So where meaning at what C values? So we're really asking, where do we get that the derivative at C, right? That's what we mean where we have a tangent line, right? That we're finding the slope of the tangent line. We want that to equal the slope of the secant line between 0, -1 and 1, 2. Great. We know how to find the slope between 2 points. It's the difference in the y's divided by the difference in the x's. We don't need to draw a picture. It'd be nice to draw a picture. I'm not like I would draw a picture totally, but it's not required. Great. 2 + 1 over 1, that's going to be 3. So we're trying to find a place where the derivative is equal to 3. So take the derivative. If it was me, I would have made this problem different, but okay. So my derivative f prime of x is going to equal 2x plus 2. So then we're going to say, okay, great. Set 2 times c plus 2 equal to 3. Subtract 2. Divide by 1/2, but divide by 2. And you get c equal to 1/2. And it is in the interval. So I will just point out, if I was asking this question, I would have done it so that when you did this part here, you would have ended up with something more like c squared equal to, I don't know, 1/4. I don't love that. Let's say, trying to pick a different number here. Fine, let's make it 4/9. Let's say c squared was 4/9. So then what are my solutions to that equation? C equals 2/3 or? Right. But our C value has to be in the original interval. So you only want to say the answers that live between the endpoints you started in. So this would not be a valid answer, because we're only asking for the values that are guaranteed by the mean value theorem that have to live in the original AB interval. So look out for that if you have a mean value theorem question, because it's certainly the way I would ask it to make sure that you really understand what's going on. Oh yeah, we only want to include the values that are actually between our A and our B, which in this case was between 0 and 1. All right, let's look at this next. Yeah, I don't love this next question. The mean value theorem is super important, but it's also kind of tedious. All right, so looking at this next one here. Let f be twice differentiable. So that means that f prime exists and f double prime exists. It also means if f is differentiable, sorry, on the interval from 0 to 2. If f is differentiable, what can we say about continuity? Is f continuous on that interval? Has to be, right? So when they tell you that a function is differentiable, you already have met the criteria for the mean value theorem, because you also automatically know it's continuous on whatever interval you're looking at. Great. Show that if f of -1 equals 2, and f of 0 equals 4, and f of 2 equals 8, then there is at least a number c in the interval from, I'm assuming he meant to write that as -1 to 2, not 1 minus to 2, such that the second derivative of c is equal to 0. Okay. This is still in the part of the problem that's about the mean value theorem, so obviously we're thinking we probably need to use the mean value theorem somehow. Okay, so here's what I'm thinking. So let's look, so here I am in the draw picture because I think it's useful. So we know that f of -1 is +2, and f of 0 is, I drew my picture poorly here. I really made my x-axis big and my y-axis small, which is kind of the opposite of what I wanted. So f of -1 is 2, f of 0 is 4, and f of 2 is 8. Sure. Something like that. So maybe my graph does, I don't know, does something like this. I don't really know. Here's what I do know. I know that somewhere between -1 and 0, the slope has to be whatever the slope of the tangent line or the secant line is, and same deal between this point and that point there. So looking just between -1 and 0, we know there must be a number, let's call it C1, such that f prime of C1 is equal to, so we're looking at the slope from that point, -1, 2, a little bit here, to that point, 0, 4. Well, that's going to be 4 minus 2 over 0 minus -1, or you could just see that the slope is 2, right? You're going over 1 and up 2. So great, there's got to be a place somewhere between -1 and 0 where the slope of the tangent line is 2. So I will point out here, I don't really know exactly what I'm doing right now. I'm just kind of moving in the direction that seems right, because they told me to show that there's a place where the second derivative is equal to 0. But to kind of, what I'm thinking I'm probably going to end up doing is applying the mean value theorem to the first derivative. So saying, oh, the first derivative equals something here, the first derivative equals something here, and then the slope of the tangent line between those 2 points is going to be like the second derivative. It's kind of weird. But I'm just kind of going with what I feel like I should be doing because I don't have a lot of other options here. So I did that. So and let me draw this picture again, less terribly. So here's my -1, here's my 0, here's my 2. So I know that somewhere between this point and that point, sorry, you can't quite see that, apologies. Somewhere between these 2 points, let's say like C1's right there, somewhere like there, the slope of the tangent line is positive 2. Let's do the same thing between this point and this point. So we're gonna say there's also got to be in the interval from 0 to 2, we're gonna have a C2 such that f prime of C2 is equal to 8 minus 4 over 2 minus 0, which is going to be 4 over 2, which is also 2. Okay, sorry. So then, okay, I see what's going to happen now. So here's what we're saying. The derivative is 2 here, and somewhere else in here, the derivative is also 2. Yeah, I guess that's true. Okay, fine. I don't love that. Fine, but that's fine. So somewhere between these 2 points, the derivative of the derivative had to be 0. Because if the derivative is equal to 2 over here, and the derivative is equal to 2 over here, and then it changes, well, this is where it'd be really good to graph the derivative instead, right? So derivative is positive. So the way I've drawn this, starting at -1, my derivative is looking positive. It's getting, let's say it's right here, and it's getting to be something like a value of 2 at C1. And then it's doing something, and then over here at C2, right? Maybe it's going to go up, or maybe it's going to go down. I don't know, but again at C2, it has to kind of hit that same value, and then it's going to do whatever after that. Well, between there and there, the derivative of my derivative flattened out, meaning the derivative of my derivative, aka the second derivative, had to equal 0. We're still just going to use the mean value theorem, though. I'm just trying to help you kind of actually see what's happening here, but you don't actually need these graphs. It's just nice to kind of think about why this is really working the way it's working. Because we're going to say, okay, great. So now, paper, come on. So now what we're going to say is, okay, well, great. Then on the interval from, let's just write it the nice way. On the interval C1 to C2, here's what we know. We know that f prime of x, the derivative, well, the function is differentiable. So f prime of x is continuous. And so is the second derivative, meaning the first derivative is differentiable, aka the second derivative exists everywhere. But those are the criteria of the mean value theorem. So we're going to say, okay, well, f prime of x is continuous, f double prime of x exists and is continuous as well. And then what we're going to say is, okay, that means that there must be some c between C1 and C2 such that the derivative of my derivative is equal to my f prime of C2 minus f prime of C1 over C2 minus C1. Again, we're just kind of going one level up with the mean value theorem. We're using it for the, instead of we're using the mean value theorem on the original function, we're using the mean value theorem on the derivative. But then, hey, look, what's f prime of C2? I know it's covered up over here, but f prime of C2 is 2. What's f prime of C1? Also 2. So that's going to have to equal 2 minus 2 over C2 minus C1, which is 0 over not 0, which is 0. And that's what we were trying to show. I don't love this question for an exam, but if it was on an exam, it is doable. It's just, it requires a lot of brain power, I feel like. You have to really think about what's going on here. So if I was taking this test and I saw that problem, I'd probably skip it and come back to it after I tried everything else. Be really honest, like if this is gonna take me more time than the points it's worth, I'm gonna go on to something else and try to get all the points I can somewhere else, doing the easier thing, and then come back to this if I have time at the end of my test. Okay, let's continue on. Let's make sure I'm not losing anything here. Type in my mind. Next page looks like it's all optimization, so we'll just skip that. No graphing on, oh, there's some graphing finally, okay. Take the intermediate value theorem. Take the IVT, which is pretty similar in nature to the MVT, at least as far as kind of the criteria. Not exactly the same, but not wholly different. So here's the intermediate value theorem. Let f be a continuous function on the interval from A to B, the closed interval from A to B. If we usually use capital N, if capital N is a number between f of A and f of B, then there must be a number C, just like in the MVT, it's got to still be between A and B. Or some people write this as A less than C less than B, such that f of C is equal to N. I do think it is worthwhile to draw a picture here because you might not be able to write this all out perfectly, but you might be able to draw a picture that kind of exactly gets at the issue. So here's what we're really saying graphically. Here's A, here's B, and we've got some function that's doing something like this. So here's my f of A, and here's my f of B. And what this theorem says is that for any value between f of A and f of B, let's say like we have a value there, let's call that our n, there must be a corresponding value between A and B that gives you that. So here, if you just draw across like this, that value right there. So there's our C. There might even be one over here as well, but I only need one. So all the theorem says that there's at least one C between A and B, so that f of C is equal to n, where n is any number between A and B. And there could be more than one, but the theorem doesn't say anything about that. It just says there's at least one. Said more generically, if your function is continuous and you have two y values, you can get any y value between those two y values. That's kind of the whole story. Let's look at the question, which is a typical question for an intermediate value theorem question. So this question says, show that there is a solution to the equation x to the fourth plus x minus 3 equal to 0 in the interval 1, 2, open. Yeah. Okay. Sometimes they won't give you an interval, but usually they will. If they don't give you an interval, your job is to make it up. So two things to say here first. Let's pretend like just for a second, they gave you this equation instead. X to the fourth plus x equal to 3. If they start you off with something where it's not equal to 0, your first job is to make it so you have an equation that's equal to 0. And then whatever stuff you have on the other side of 0, give that a name. So I would start off after making sure everything was equal to 0. We're going to say, great, let f of x equal the function that we're trying to show has a solution to be equal to 0. That's a very important first step. It makes it so much easier to do the rest of this problem. I think it's important to at least state or point out or observe, I think is the word I've chosen to be the best. Observe that your function f of x is in fact continuous. This one's continuous everywhere. We only are concerned with it being continuous on the closed interval from 1 to 2. But note, right, f of x is continuous everywhere. It's a polynomial. That's all you need to say. You probably don't even have to say that. If you just say, hey, look, you can look at that function, I can look at that function, we both know that function is continuous everywhere because it's a polynomial. You just have to like really saying this is enough. No one's gonna fight you on that. Be like, yeah, of course it's continuous, it's a polynomial. Sure, that'll also be fine for this function, right? Because of the polynomial. But I'm putting the domain that I know I'm talking about because that's the I don't know, the more correct way. No, not more correct is a bad thing to say there. It's just the way I think about doing it. So, but right, in the solutions here, he writes let f of x equal x to the fourth plus x minus 3, and then he writes f is continuous. That's it. No, we're not done yet. I'm just saying these are the things you should do first. You should say that f of x is whatever the equation is that's supposed to equal 0. And if it's not equal to 0, you should start off by making it equal to 0. And then part 2, state that. Don't try to prove that. Just say, yeah, f of x is continuous. It's and make sure it actually is like in your head, like, oh yeah, it's a polynomial, good. Or if your function was something like f of x equal to, I don't know, 1 over x, then it would be a good idea to just say it's continuous on the interval you're interested in, because 1 over x is not continuous for all reals. It's definitely not continuous at 0. So that's when you would be a little bit more cagey and say, okay, yeah, f of x is continuous on the closed interval that we know we have to deal with here. Great. Then you have to look for 2 things. And typically it's just plugging in your endpoints. Observe that f of 1 is equal to 1 plus 1 minus 3. I don't actually care that it's negative 1. I just care that it's negative. Similarly, f of 2, f of 2 is 16 plus 2 minus 3. Again, I don't really care that it's 15. I just care that it's positive. So if the function goes from a negative number to a positive number, it has to go through 0 by the intermediate value theorem. So we can then say, I like to write words like, then by the intermediate value theorem, you should abbreviate that. Since f of x is continuous and f of 1 is negative and f of 2 is positive, there must be a number c between 1 and 2 such that f of c, which would be c to the 4th plus c minus 3, is equal to 0. Sorry, I can't see that, apologies. And that's it. We showed that there is a solution. We did not find the solution and we can't find the solution, right? These problems, when they say to show that there is a solution, your job is almost never to actually find the solution. Your job is to use the intermediate value theorem to display that there has to be a solution somewhere between 1 and 2, and that's it. All right, keep going. Find the Taylor polynomial of degree 5. Taylor polynomial, degree 5. It's a little bit much. For f of x equal to x plus x squared plus sine of x centered at 0. Oh, good. Bless you. at a equal to 0. So here's what we know we're going to need. We know we're going to need the derivatives of this function up to the fifth derivative. So I would probably start by writing down my derivatives. So my function is x plus x squared plus sine x. My first derivative is 1 plus 2x plus cosine x. My second derivative is 2 minus sine x. My third derivative is going to be negative cosine x. My fourth derivative is going to be positive sine x. And my fifth derivative is going to be cosine x. And then we actually don't really care so much about those as plugging in the center to each of those. So if we actually plug in a equal to 0, we're going to get that f of 0 is 0 plus 0 plus sine of 0 is 0. And f prime of 0 is 1 plus 0 plus cosine of 0 is 1. 1 plus 1, which is 2. And f double prime of 0 is going to be 2 minus 0, which is 2. And f triple prime of 0 is going to be negative cosine of 0, which is negative 1. And the fourth derivative at 0 is 0. And the fifth derivative at 0 is 1. And then we have to remember what the formula is for the Taylor polynomial. So here's the pattern. My fifth degree Taylor polynomial is going to equal, I'm going to write out the general formula first. It's going to be f of a plus f prime of a times x minus a plus f double prime of a divided by 2 factorial times x minus a squared. And following the same pattern, you should be able to write out the next three terms, right? Just the next derivative divided by the next factorial times the next power of x minus a. So it's going to be f triple prime of a over 3 factorial times x minus a cubed plus the fourth derivative at a over 4 factorial times x minus a to the fourth. Finally, the fifth derivative at a over 5 factorial times x minus a to the fifth. In this particular case, we're just going to plug in all the values. That's why we did the work of finding all these values here. I'm going to write it out kind of annoyingly, but then we'll maybe simplify it. So it's going to be 0 plus 2 times x minus 0 plus, those are both 2. That's surprising. Okay, yeah. Plus another 2 over 2 factorial times x minus 0 squared plus the third derivative, which was negative 1 over 3 factorial times x cubed plus the fourth derivative, which was 0. So for this fourth term here, I don't really need to write anything because once that's 0, 0 divided by 4 factorial times x to the fourth is still just all going to become 0. And finally, we have a 1 over 5 factorial times x to the fifth power. And really, you could probably just leave it like that. If you really wanted to simplify it a tiny bit, you can write it as 2x plus 2 over 2 factorial x squared minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. And yeah, there's more simplification that could be done, but you should not do it. Right? You're not going to get points for writing that 2 over 2 factorial is equal to 1, even though it's an easy simplification, right? Certainly in the solutions, he didn't do that. Times 11:30. Okay. Extra credit. Extra credit is just code for I can write a problem as hard as I want to write, and you can't stop me because it's extra credit. So you can just skip it if you want to. But usually extra problems are not too heinous. That's debatable. I feel like we've done this problem. Oh no, we haven't. Okay. So there's 2 extra credit problems. So part A. Sketch the graph of a function with the following properties. So we want a graph with the following properties. So f has a vertical asymptote at x equal, sorry, 1 second. Has a vertical asymptote at x equals 0. That's 1. We have that f of 1 equals 2. F of -1 equals -2. F prime of 1 equals f prime of -1 equals 0. And we know that f double prime of x is negative on the left side of the graph, and f double prime of x is positive on the right side of the graph. And gosh, there's so much. So here's a better way to, so if I was doing this, I would actually not write this. I would do the following instead. I would reframe this as just saying, oh, my second derivative number line is negative over here and positive over here, meaning I'm going to be concave down, concave up. Similarly, my first derivative, he says it's positive on negative infinity to -1 and 1 to infinity. So he's saying for my first derivative, it's positive over here and over here. And then it's negative from -1 to 0 and 0 to 1. And he does break it up because we have a vertical asymptote at 0. So it can't be just the whole thing. So that means graphically, my function is increasing, decreasing, decreasing, increasing. I think it's much more useful to write it this way for myself because it's going to help me draw the picture. Okay, so now we're going to try and graph this thing. My vertical asymptote's right there. I'm not going to like draw it again because it's on the axis. And then I know I have at the point 1, 2. Well, I have the point 1, 2. And similarly, I have the point -1, -2. And I know a couple things. I know that the function's concave up over here. I also know that I have a vertical asymptote here. And if I have a vertical asymptote at 0, and the function is decreasing just after to the right of that, I know it has to be coming from that direction there. I have no other choice. To the right of 0, the function is decreasing, at least immediately, and it's a vertical asymptote. So I had to be coming from a positive infinity, decreasing, decreasing, decreasing until I get to that relative minimum. And then after that, I have to be increasing, but still concave up. They don't like turn around. And then kind of the opposite on the left side, right? From the left, it's decreasing after this maximum like that to my vertical asymptote. And then on the other side of it, it's increasing towards it. So increasing, hit my relative maximum of -1, -2, and then decrease afterwards. If you wanted to be extra spicy about it, he could have thrown in the fact that the function should look like it's an odd function. Because it is an odd function, at least the way we've drawn it. Yeah, this feels a little, I don't know. It doesn't feel easy, but it feels like it could have been harder. Like, I feel like this one was, there could have been more going on here. Like, if I was doing this problem, I would have thrown in some horizontal asymptote stuff. Like, maybe so you had to deal with the horizontal asymptote as well. But then the concavity would have had to have changed. So, yeah. All right. Who could have slant asymptote? Slant asymptote at y equals x. There it is. We already kind of made it happen, right? Okay, so anyway. That one's not my favorite. Let's look at the next one. I feel like we've kind of done a problem similar to this in class, but it's still good to do more. So I will point out, this practice exam does not have any graphing. Right? Have we had a graphing problem yet? I mean, aside from the one we just did, nothing else was really like graph a function. Right? Right, exactly. So after we do this last problem that says, I think we should try to hit some graphing problems. So let's look at this function here. Well, this is a graphing problem as well. So f of x equals, no, it's not a graphing problem. He graphed it, but it doesn't say to graph it. So f of x equals 4x minus 6x to the 2/3. Find all relative extrema and inflection points. Ooh, I'm curious. Yeah, so I would point out, you do not need to graph this, right? The question does not say to graph it, so don't graph it. So relative extrema, usual deal, we're gonna find the first derivative. We're gonna take it's gonna be 4 minus 6 times 2/3 times x to the negative 1/3, which simplifies to 4 minus 4 times x to the negative 1/3. There's, I don't know the best way to think about doing this, to be perfectly honest. I would probably start by factoring out a 4. We have 1 minus x to the negative 1/3, and then I'd probably just rewrite it as 4 times 1 minus 1 over x to the 1/3. And while you could get a common denominator here, I also think the numbers here are easy enough that you could probably just guess what your critical value is that makes this whole thing equal to 0. So I want 1 minus 1 over this to equal 0. Well, great. That means x to the 1/3 had better equal what? 1. And if x to the 1/3 equals 1, then x better be 1, right? There's not a lot of the other things to guess here. So this, if we set this equal to 0, we're going to get x equal to 1. If we set this equal to being undefined, which I don't love saying equals undefined, but okay, you're going to get x equal to 0, because if x is 0, you have division by 0, and that makes this derivative undefined. So those are both real critical values that we have to consider in our number line for our first derivative. Here is where I'm regretting not doing the thing. So there's a good reason to do more work here. And the reason is that when you do your critical values on your number line, it is best to have this thing fully factored. And it is not fully factored the way I've written it, because it's not clear to me that when I plug in a certain value of x, the product's going to be positive or negative. I don't want to have to subtract. Right? I don't want to have to think about what 1 minus 1 over whatever my thing actually is. So here's what I should do. I should rewrite this as 4 times, I'm going to get a common denominator. So it's going to be x to the 1/3 over x to the 1/3 minus 1 over x to the 1/3. And then I'm going to rewrite this as 4 times x to the 1/3 minus 1 over x to the 1/3. It's still not amazing, but it's a little bit better to think about this way. Technically, there's more weird factoring you could do if you were compelled to, but you should not. So, let's see. Pick a number larger than 1, like 8. 8's a great choice here because we know the key root of 8 is 2. 2 minus 1 is positive. 2 is positive. Positive over positive is positive. Pick a number between 0 and 1. I don't know what I'm picking, but a number less than 1 to the 1/3 is still less than 1, and subtracting 1 is going to be negative. Bottom's going to be positive. Whole thing's negative. Finally, pick a number that's negative, like -1. Okay, what's the key root of -1? -1. We can always take an odd root of any positive or negative number. Cube root of -1 is -1. Cube root of -8 is -2. Because -2 times -2 times -2 is -8. -1 times -1 times -1 is -1. So if you plug in the -8, for example, you're going to get -2 minus 1, which is negative, and the -2, which is negative, and the whole thing's positive. So we are increasing, decreasing, increasing. So it looks like we have a relative maximum at, curious what he said here. Yeah, I just want to know how much work he did. Sure. I would have said at 0, 0, because if I plug in 0 to my original function, right, that's my f of 0. And a relative minimum at 1, if I plug in 1 here, 4 times 1 minus 6 times 1 is going to be -2. I guess he did graph them, so okay. Then the inflection points. I don't think there are any. Let's check and see anyway. So, no, I won't say that. Yeah, I have to reframe how I think of inflection points. The second derivative, taking the derivative of the first derivative, which is 4 minus 4 times x to the -1/3, you're going to get positive 4/3 times x to the -4/3, which is never equal to 0. But if you rewrite it as 4 over 3 times x to the 4/3, you can see that it is undefined when x is equal to 0. So we could potentially have an inflection point at 0. Let's check and see. Checking our second derivative here, making it bigger than 0, like 1. 1 to any power is 1. So 1 to the 4/3 is 1, and 4/3 times 1 is positive. Let's check something like -1. You have to be extra careful here. -1 to the 4/3 power is going to be +1. Taking the cube root, which is -1, but the -1 to the 4th is +1. So it's also positive over here, which means we're concave up. We have no inflection point, because the concavity doesn't change. All right. What else do I have here? Let's see. You have a good graphing problem, right? Oh yeah, let's do that one. Yeah, sure. I don't love that one, actually. Don't love all these. No. Want to give you something else. Let me grab that one instead. I'll drop off my paper. Sorry, one moment, please. Unless there's something else that you have a burning question about. Yeah. Uh-huh.
Are we expected to know arctan?
Yes, you're expected to know that the derivative of the arc tangent of x is equal to 1 over x squared plus 1. And so more generally, the derivative of the arc tangent of some stuff like x cubed times sine of x would be 1 over the stuff squared plus 1 times the what of the stuff? The derivative of the stuff. So we have to use the product rule and get 3x squared times sine of x plus x cubed times cosine of x. Yeah. I don't think there's enough time for another graph.
Yesterday I asked him in class, like, so he showed us the second derivative test,
Mm-hmm.
and then at some point it failed, but we still had a relative min.
Right,
So that if it just fails, we can still check if there is a relative min.
right. So if the second derivative test fails, it means we literally don't know. But we can, so here's what I'll tell you. The first derivative test is superior. The first derivative test will always show you whether you have a relative max, a relative min, or neither at critical points in the first derivative. There are reasons the second derivative test is nice, and occasionally we use it, especially when we talk about optimization in section 4.4. There are often times when it's just like, it's easier just to use the second derivative test to see if something gives you a maximum or a minimum. But especially graphically, you almost always want to be using the first derivative test to see if you have a relative maximum, relative minimum. Yeah. Sure. So absolute relative error. Just trying to think of a good example here. Sure, so let's look at the following. If you want to estimate the, sure, let's talk about the error in the volume of a cylinder of height 5 if the radius is measured to be 3 centimeters with a potential error of plus or minus 0.3 centimeters. Kind of a big error, right? Like 10% error, that's not small. Okay, so yeah. Let's talk about what the volume would be. I feel like I'm not gonna have enough room here. So what I'm really thinking about with this kind of problem is how it relates to a linearization. That's kind of, because the linearization is really the context for estimating the amount of something. So let's reframe this as we want to estimate the volume of a cylinder with height equal to 5 inches and a radius equal to 3 centimeters, but then we're going to add on plus or minus 0.3 centimeters. Okay, which I know might not feel different to you, but it feels different to me. Here's my cylinder, got a radius of 3 centimeters. It's got a height of 5 centimeters. I didn't actually write any units there, apologies. 5 centimeters. I think I said inches before, which is terrible. So I will point out that the volume of this cylinder as a function of the only thing that's changing. So normally we'd say the volume of a cylinder was pi r squared times h. And you have 2 variables in there. But the height we're just saying is 5 and it's not changing. So here the volume as a function of the radius is pi times the radius squared times 5. And then what I'm going to do is I'm going to try to get a linearization for this function at a radius of 3 inches. Because that's like the nice value I have. Then we're going to say, great, well, we know how to do this linearization thing. Our linearization, L of R, is going to be V of 3 plus V prime of 3 times R minus 3. Just the usual equation, but instead of writing F of A plus F prime of A times X minus A, I've changed my X's to R's and my A's to the value I'm actually using, which is 3. Okay, so now let's plug in, I guess I should find the derivative here. V prime of R is going to be, the derivative of this is going to be 10 times pi times R. And then my V prime of 3 is going to be 30 pi. And we already know that our V of 3 is going to be 5 times pi times 3 squared, which is 45 pi. So here's what we've got. Our linearization is going to be 45 pi plus, that's a pretty strong derivative there, 30 pi times R minus 3. So then, if we want to estimate the volume at, and I always kind of go with the bigger value. So the volume when the radius is 3.3 centimeters would be approximately the linearization when we plug in 3.3 centimeters, which is the original volume of 45 pi cubic centimeters plus our estimate in the error, essentially. That's going to be 45 pi plus, that's going to be 0.3. 0.3 times 30 is going to be 9. Okay, so depending on what's being asked, we have to be careful how we answer this, right? And I kind of actually rephrase the question in a slightly wrong way, because the original question was estimate the error in the volume, and then the thing I rewrote here was estimate the volume, which is not the same thing. So this is our estimate of the volume. The volume of a cylinder with a radius of 3.3 is approximately 54 pi cubic centimeters. But the error is just this part here. So this is our error estimate. As much as plus or minus 9 pi cubic centimeters. So our error estimate is up to 9 pi. Either way, right? Because this could have been 3.3 minus 3, or it could have been the other direction, 2.7 minus 3, if we got minus 0.3. So there's our actual error estimate. The relative error estimate is taking your absolute error estimate and dividing it by the actual value of the thing you're estimating. So our relative error in this case would be 9 pi divided by 45 pi. Which is equal to 1/5. Or 0.2. Because so when you're finding the relative error, you're saying, so it's essentially like it's like relative it's like the relative growth rate in population. Right? When we talk about the growth rate, we're saying the population is growing at like maybe 1,000 people per year. But the relative growth rate is it's growing at 1,000 people per year per the population size. So when we talk about the relative error, it's the error in the volume divided by whatever the total volume is. And my total volume was, I believe, right? It was, yeah, 45 pi. So let me give me one more second here. I'll point out that my relative error for the radius, right? The relative error for the radius is 0.3 divided by 3, which is just going to be 0.1 or 10%. And essentially, and this is not coincidental, since the radius is getting squared here, we're doubling the error. So here, our error is up to a maximum of 20%. If this had been a sphere instead, or I should say, no, if this had been a sphere where the radius was getting cubed, we would have ended up tripling our error up to a maximum of 30%. And there's always this kind of dimensional thing that always happens where essentially if you're increasing by some factor of dimensionality, like from a one-dimensional thing to a three-dimensional thing, you're tripling your error. You're going from a one-dimensional thing to a two-dimensional thing, you're doubling your error. The reason it's doubling here is because there isn't any error in the third dimension of height. So that's why it's only doubling here. Hopefully that helped make it clearer and not more confusing, I hope. But that's kind of the idea with relative error versus absolute error. Absolute error is just the raw number. Relative error is that raw number divided by the actual value of the thing you're trying to measure. And then percent error is take that decimal and multiply it by 100 to make it a percentage. All right. Good luck on your exam.